Okay, from the previous lesson, okay, we touched base with the interaction between magnetic field, the magnet, and the current. How these two, when they are placed together, let's say at a condition, let's say they are right angle to each other, they will actually induce a force, a third party. And how do I identify the direction of this third party, this force induced? I will actually, we touch base with Fleming left-hand rule, and we have also touched base with Maxwell, using Maxwell magnetic field lines. Okay, and from our last lesson, when we talk about Maxwell left-hand rule, Fleming left-hand rule, we look at the usage, how we use the fingers, how each fingers represent each of them to get the correct direction of force induced. We also look at the keywords of using it, of writing Fleming left-hand rule. How do we portray the correct understanding to the marker? Now, from that on, okay, in this topic, we will take one step further to see, after we produce the force induced, what are we going to use with that force? What are the applications of using force induced? After creating the force induced, how am I going to use, or what am I going to use it on? Okay, how useful is it? Okay, and this section here, we talk about one particular effect, which is the turning effect of a current. Okay, now in your simplified version, okay, in the simplified version, after using your Maxwell rule, okay, it could be a case like this, whereby I have your current going through. This is your current upwards. Your field line is north to south, so it will be this pointing to the right. Okay, so this is your north, this is your south. Your current, let's say if I look at the left hand side now, okay, if I look at the left hand side, my current will be upwards. Okay, so when you put these two together, so what do I do now is this. Okay, when my current is upwards, okay, so now when my current is upwards, okay, now you'll find that there are certain things will happen in your Fleming left-hand rule. If I have a force induced, which is the current is upwards, force field current. So my field is pointing from north to south. So my field is pointing to the right. My current is upwards. Okay, so now you'll find that my current is upwards. Okay, so if you look at the question here, is my field is pointing to the right. Okay, my current is pointing upwards. If you let go of your thumb, you'll find that your thumb will point the force into your computer screen, which is what I written here. The force induced will be pushing the coil inwards. Okay, so the orientation of the fingers, okay, you need to take note of the orientation. So your field is north to south, current is upwards, okay, in this case upwards. Force is, like your thumb, your force will be pointing towards the screen. Okay, so for the left side, for current AB, in the rod AB, the current is flowing upwards. Okay, you'll find that the force induced will actually be pointing towards or pushing towards inwards. Okay, so the force will be this direction. Oh, cannot see. Okay, let me change the color first. Okay, the force will be this side. Okay, this will be the force induced. Okay, so similarly, if you look at on the other side here, if you reverse the thing here, same thing, your field is north to south. Now your current is from C to D. Your current is downwards. If you let go of your thumb, okay, you will point towards you. It will point outwards. Okay, you're pushing the rod CD outwards. So the force here will be outwards. And what is the ultimate combination whereby one side of the rod, so let's say if I have the rod here, so one side of the force pushes in, one side of the force pushes out. So you'll find that if I push in, the coil will start to rotate. Yeah, I will push in, this side will push out, so it will start to rotate. Okay, so you have this rotation effect that will take place, and what we call the turning effect. And this turning effect is important because it's one of the foundation of some of the applications that we are looking at. Okay, so again, if you look at the cross-section view, okay, of that particular picture here, you will find that if you have two rods, okay, the square rod, so now instead of looking at the rod at the front surface, I'll look at the side view. The side view, it looks like what you see on the screen. Okay, so I have a force, the current is outwards, means towards you. So the current is towards your force, field, current. So the middle finger is pointing towards you. Okay, so the middle finger is pointing towards you. Okay, then after that, field is north to south, to the right. Okay, you let go of your thumb, you'll find that the force will be pointing upwards. Same thing, you do the same for the reverse or for the other side of the rod. The other side of the rod, the current is into the paper. Okay, if you use Fermi left hand rule, you'll find that the force will be pointing downwards. So you find that on the left side of the rod, the force is upwards. Right side of the rod, the force is downwards. So you'll find that the object will actually rotate. The object will actually rotate, or the coil will actually rotate what we call clockwise. Okay, and this is what we mean by the moments. Okay, clockwise. Okay. Now, same thing, if you look at the usage, okay, if you look at the effects, okay, the turning effect is the same as what we mentioned in your Maxwell rule. Okay, I can increase the magnetic effect, I can increase the turning effect. They all usually have the same particular factors. I can increase the number of turns of coil. I can increase the wire coil. Okay, in this case here, sometimes I might even put a iron core inside. Okay, so I can actually put iron core inside. Now, what is the common usage? The small users, it could be used for ammeter, voltmeter. Okay, for ammeter and voltmeter. Okay, whereby this is your north pole, this is your south pole, and you look at the particular question here. Okay, so right now, same situation, you'll find that at this particular case, if I have a current that's flowing inwards into the coil and the current is flowing out of the coil, north to south, my field line is this side. My field line is pointing to the right. If my current is coming out towards you, you'll find that the force induced will be upwards. On the other rod, if my current is going out, you'll find that the force induced will be downwards. So as a result, what will happen to this coil here, left side will be pushed up, right side will push down. So indirectly, what happened to this needle here? This needle will be rotated. So I can actually make this needle swing. So this is how voltmeter and ammeter works. Whenever I click this voltmeter to the circuit, current will pass through the voltmeter, it will pass through the coil, to be exact, the coil here. Okay, and when the current flows through the coil, the presence of the magnet inside the meter will cause a force induced to be induced on the coil. And this force induced will actually turn the coil and it will swing it to any reading that you need, okay, or it will measure. And that's how the voltmeter and ammeter works. The other way of doing it is whereby you actually uses a DC motor. If you run the same principle as your voltmeter and ammeter, whereby it uses the current and produce a turning effect. Common thing about this DC motor, I can sometimes in other countries I can use it to actually turn something. Example, I can use it to winch wires. So example, I have a winch, okay, which is a motor with a cable. So what I do is I hook onto another car. So if I want to pull the car towards me, what I do, I hinge it there, I will activate my motor. So what does this motor do is, inside this motor there is coil, there's a coil inside where the current will flow through, and there is a gigantic magnet inside there also. So when I switch on the current and the coil will behave like this. Okay, the current and the field line will interact and the force induced will appear. And the force will be induced onto the winch itself to wind the cable, inward towards me. So when I winch the cable in, to wind the cable in, the car will be pulled in. So that's how DC motor works, okay, to convert electrical energy to mechanical energy. There are numerous applications, but these are one of the common examples that you actually see in our day-to-day lives. Okay, there are other things that I can actually use it for lifts, for escalators, etc., whereby I actually uses current, I uses electricity to actually produce forces. Okay, what we call the induced force. Okay, so now it's a short topic here. We look at primarily the applications. There's a lot of applications, but the common thing about this application is it runs on the fact that it uses the turning effect, okay, of forces. Okay, the turning effect on the coil. Okay, and because of once I use of turning effect, there are numerous examples on it. So there isn't one that you have to memorize. It's just that I will give you any one that you have to, and during the exam or during the question, the test day, you have to analyze the questions. But no matter what, all the turning effect of the coils, interactions of the force induced that produce turning effect, they all come from the same tree. They all come from the same concept, okay, which is the interaction between your current, magnetic field lines, whereby it produces what we call a force induced. Okay, and what's the condition? Perpendicular. And you, same thing like I mentioned before in the previous section, you need to know the keywords and you need to know the usage of Fleming left-hand rule. Okay, you have to know it very well. You have to know how to use Fleming left-hand rule every time at any time, such that you will get the answer correctly. And from then on, you will know how to explain your answer using the right keywords. And that's the first cut. And the second cut is once you have that particular answers, you're going to build up to the next level. The next level you're going on to look at is the turning effect, the applications. How do you use the force induced? How do you use the force induced to actually to actually do certain action, to achieve certain action or to achieve certain behavior? It could be simple thing like rotations. Okay, it could be simple thing like winching. Okay, the rotation effect. How are you going to use it? How are you going to explain to the marker? Okay, so all these right on the very, very basic things of understanding what is Fleming left-hand rule. So like I mentioned in the previous topic, in the previous video, if your Fleming left-hand rule, the usage of Fleming left-hand rule or the explanation of Fleming left-hand rule is still unsure, there's still a bit of gaps, remember to refer back to the video, rewatch the video, or you can run through your textbooks or your notes to get a better understanding or clearer understanding, because textbook and notes, they tend to give better explanations because of the words. They can use much more words than the 15 minutes video that I created for you. Okay, if not, remember to go back to your physics teacher, because all physics teachers are quite well versed in this topic. You can actually look for them for explanations. Okay, and of course, the common way, they are always welcome. Okay, you can leave your comments and you can leave your questions at the comment bar. I will try my best to get back to you ASAP. Okay, if not, okay, this will be the last topic on chapter 18, which also coincidentally will be the last topic for our combined science syllabus in Sec 4. Okay, so with this, okay, remember, once you finish this particular topic, remember to rewind or revise all the videos that you have watched. Even for this particular topic, just revisit the topic, make sure all the gaps are filled, all the gaps are closed. After that, you can start your revisions or you start your revision for this topic. If you have done this, good. If not, okay, if you've done this, yes, then the next thing that you look forward is actually to re-look at the gaps in other topics. If you have gaps in other topics that you can be solved, or I can help you using through my videos, or me myself, come and look for me or rewatch the video, or you can look for your teachers, or you can reread your textbook to fill out the gaps, because it's utmost important to fill up all the gaps that you have for these 2 years. The topics covered in these 2 years: 18 topics for combined science, okay, 22 topics for pure science. Okay, it's important to fill out the gaps so that you can actually better prepare yourself for revisions, practicing on paper, eliciting the best information from all the revisions. Okay, if not, okay, this is where I end off. And of course, see you in class. Okay, enjoy your days. See you. Bye-bye.